Alright, this is a long one, so if you're in a rush, use the chapters below. The first half of the video is a summary of the VLX3, results from testing we did, and my analysis of thoroughly picking apart that data from that test. The second half is an interview I did with Rebecca Clark over at NavVis that's chock full of advice on how to get the most of your VLX or MLX. This is the first episode of a multi-part series where I'll be exploring and comparing other SLAM scanners on the same test site. The subsequent episodes will be building off of this first one, where there will be more apples to apples comparisons, but this episode was already getting so long I just wanted to focus on the VLX today. Now, just in case any of you have been living under a rock and aren't familiar with NavVis's VLX3, it's a wearable 3D SLAM scanner. One of the features that sets the VLX apart from the majority of its competition is the fact it has LiDAR sensors mounted perpendicularly to each other. One on the chest that captures a vertical 40-degree swath of floor-to-ceiling data, and one overhead that captures a horizontal swath of points that fill in the missed data from the chest sensor. The dual sensors do a fantastic job of maximizing scan coverage compared to single sensor units. They use the well-known and trusted Hesai XT32 LiDAR pucks that are capable of 640,000 single return points per second per sensor for a combined potential point capture of nearly 1.3 million points per second. The XT32 has a range of 80 meters on surfaces with 10% reflectivity, and according to Hesai's testing scheme, it has a range accuracy of plus or minus 1 centimeter and a range precision of plus or minus half a centimeter. Now, this does not mean the VLX has 1 centimeter accuracy, but more on that later. Even though the XT32 has a range of 80 meters, NavVis quotes a 50 meter operational range for the VLX3 with a 5 millimeter local accuracy of the processed point cloud. You get 1.5 hours of scan time from the two hot swappable batteries, and something I thought was really cool that NavVis did was use a battery mount that isn't proprietary, and they even go as far as recommending third-party providers for people wanting to save a few bucks on replacement batteries. They also use a portable USB-C Type-C hard drive that isn't proprietary, meaning you can pick up extra storage from a local Best Buy or Walmart. A very ethical choice and a far cry from Leica RTC's $1,600 256 gigabyte USB hard drive. The VLX3 weighs in at about 20 pounds, but since it does a great job of sharing that weight between the shoulders and the belt, it really isn't taxing to scan long periods with it. We've had plenty of 8+ hour back-to-back scan days where user fatigue was a non-issue. The Pelican case it comes in is well thought out and contains everything you need to scan a site. But this is a big scanner. It folds up into a somewhat compact package, but it's still pretty big. We do a ton of travel work and size is a consideration, especially compared to an RTC that I can fit on my back and it fits into the overhead bin on an airplane. Our VLX, on the other hand, gets dinged as oversized luggage when we fly, which adds cost and hassle. For all of you familiar with the plethora of SLAM units in the industry right now, when you think of a NavVis dataset, what's the first thing you think of? For me, it's one word: beautiful. Accuracy, data density, cost, all of that aside for the moment. It's hard to find a better looking dataset than what you get from a VLX. They're just beautiful. 100% king of the hill in that respect, in my opinion. On the hardware side, they accomplish this with 4 20 megapixel cameras, each utilizing a relatively large 1-inch sensor that can either be operated manually through a button on the VLX or that can be set to take images automatically at a set distance walked. If you know a thing or two about cameras, you know sensor size has a huge impact on the quality of image, and I think that having 4 1-inch sensors was a good play on NavVis's part. Beyond just the quality of the sensor they use, they're also doing a lot of computations behind the scene to get that visually appealing point cloud. After the user captures data in the field with either the VLX or NavVis's MLX, the raw scan data is brought into their cloud-based processing software. Now, this is where things can get a bit contentious. I'm not going to sit here and say everyone loves Ivion and it's the best thing since sliced bread. Like most things in this world, it comes with pros and cons, but in my opinion, the pros outweigh the cons, especially given the news I'm going to talk about in just a minute. First of all, let's just talk about the elephant in the room. It's a token-based pay-to-play software. Now, I covered a lot of this in my MLX review video, so I'll try not to beat a dead horse, but it's a massive consideration when deciding on a new scanner. Every time you scan something, it's going to cost you to process that data. However, let's be fair, it's not as simple as I have to pay every time I use my VLX, and since I already paid for, let's say, Riscan, if I'm using my VZ600, it's free from here on out. There are actually a lot of ways using Ivion can save you money. You don't have to shell out an upfront cost to buy the software, which typically also comes with either a yearly maintenance fee or it's just a straight up subscription you have to renew every year. And it's easy to forget these $5,000, $8,000, $10,000 processing computers need maintenance and rarely run issue free for years on end. There are hidden costs to processing locally. Using Ivion, you also get all the other advantages that come with cloud processing, such as parallel processing, ease of scalability, accessibility, and Ivion is just downright dead simple to process and deliver data with. You can fly out to a job, capture your data, upload it to the cloud using any regular laptop, and by the time you fly home and wake up the next day, there's a good chance you could have a process point cloud waiting for you that can be delivered to the client through Ivion's web sharing abilities. But it's not all roses and sunshine. Being that you need to pay every single time you process scan data, this can make testing and practicing with your equipment cost prohibitive. As someone that obviously loves to run tests and figure out what works and what doesn't, this annoys me. I have no way to sugarcoat that. Perhaps in the future, they could introduce a testing mode that allows people to collect data, process it, but not export it or limit the exports in some respects so it can be used for commercial purposes. I don't know exactly how that would work, but coming from a customer, I would really appreciate it, as I'm sure others would too. Speaking of testing, when it comes to getting into the nitty-gritty details and settings of Ivion, there isn't a significant amount of control one has in processing the data. You more or less upload your data, apply control if you used it, and if you took multiple overlapping data sets, merge those and you're done. But if things go wrong and you need to address issues, there aren't a ton of tools you have available to you. There are a few settings you can adjust, and you can chop up a trajectory if there are problem areas of your walk, but you have relatively little control of how the data gets processed. Now, this is good and bad. For people that don't want to dive headfirst into the weeds, it makes for a simple, easy, and straightforward process. But it can be frustrating for people that want to manipulate the settings to get optimal results if everything didn't work perfectly with the base settings, or if someone wants more control over how the points are filtered. All right, let's jump into the accuracy test. For any of those that missed my Riegl VZ600i versus Leica RTC360 video, I'll do a quick recap of the testing site and procedure, but I would recommend checking out that video as well for a more thorough explanation, or my one-dimensional method of measuring point cloud accuracy video. The test site was a 3-story parking garage of more than 250,000 square feet. I have about 15 control points established on each floor, along with a combined total of well over 100 independent check shots. The survey control network was created using what would normally be considered an over-the-top amount of redundancy. The extra effort was put in to make sure we are measuring the accuracy of the point cloud as best we can. Each control point and check shot had standard deviations of under 3 millimeters after being processed using a least squares adjustment in StarNet. I invited NavVis out to perform the data capture on this site, and you may recognize Frank Hannell as the man operating the VLX3. He was also the one that captured the test site for the MLX video I did. I gave Frank full reign to use as many or as few control points as he wished, knowing he has extensive experience with the VLX, and he would know much better than most how much control was optimal. NavVis also handled the processing of the raw scan data. It took Frank just under 3 hours to capture the entire site via 3 different datasets, and he ended up using about 7 control points per floor. Now I have to say, this is a beautiful point cloud. There aren't gaps in the data, there is next to no overspray on corners, there's an even density throughout, and the colorization is top tier. On the surface, it looks flawless. But is it? If you've been in this industry long enough, you've probably seen hundreds of these animations showing amazing datasets with captions of how perfect they are, how innovative the technology is that made them, with a few buzzwords like game changer and insights thrown in for good measure. While these animations are a fantastic tool of showing off data, shout out to Nubagon, they do little to show any measure of accuracy or data integrity and can be exceptional at hiding flaws in the data. Now, this isn't a jab at the animation software in any way. It's doing exactly what we would want it to do, making almost any dataset look fantastic. It's more of a point that a distant screen grab or an X-rayed animation doesn't really tell us a thing about the quality of a dataset. If you really want to post an impressive little video, do a screen recording of you ripping through a bunch of cross-sections of your dataset. That's where the flaws show themselves. And unfortunately, once I did that here, I found those flaws almost immediately. And not a couple of minor issues, there were consistent issues across the entire site to a point where I would certainly be hesitant delivering this dataset to a client. To gauge the validity of data, the very first thing I do when running quality control on a point cloud is to start cutting cross-sections. This is an extremely important step in running the quality control on data. I'll do another quick shout out to NForce here. Hands down, the best tool I've ever used for this. If NForce didn't do anything else, I would own it just for its exceptional sectioning and visualization capabilities. Not to spill the beans, but so far for this mini series, I've QC'd 3 different SLAM datasets from 3 different manufacturers, all of which knew I would be showing each of their data publicly that would be seen by tens of thousands of people in the industry, so you would assume they would have QC'd their point clouds before delivering it to me. All 3 datasets came back with issues large enough where I wouldn't have sent any one of them to a client. All this is to say, I'm willing to bet if they had NForce to section their data, they would have caught those issues before they ever made it to me. And this is not unique to this situation. It's wild what I can catch in NForce that made it past other QC from other software. In this dataset, I found several examples of duplicated walls, floors, and ceilings. Some duplications were well over an inch out, others were less. The problem is when it comes time to digitize or model this dataset, which wall, floor, or ceiling is the right one? Or is neither the right one and the true value is somewhere in the middle? Who knows? Usually you can infer with terrestrial scan data because it's often one scan position of points that's out, but it's much more difficult with SLAM data. Now, to be fair here, what we're looking at certainly isn't uncommon with point clouds from SLAM scanners. When this happens with terrestrial scan data, it's typically an easy fix. It's often caused by a number of scans, it could be one, it could be more, not aligning to a satisfactory level with other nearby scans. It's often caught in the registration process and can be as simple as identifying the problem scan and manually adjusting its registration. When we're dealing with SLAM, it can be caused by either misalignment of one dataset to another or the failure of the SLAM algorithm to merge points in an area that was scanned multiple times within the same dataset. In my experience with a VLX, I often see the first situation as the culprit of this issue. This is because currently Ivion relies on a rigid adjustment between datasets. If the 2 datasets you're trying to align to each other don't perfectly match, this is what you're going to get, which kind of sucks. I would prefer that the datasets would talk to each other and a non-rigid adjustment between individual datasets was an option given that these datasets can span very large areas and do contain drift and error. A rigid alignment works great where we merge two terrestrial scans together. There is generally very little error in a single terrestrial scan, but when we're talking about a 60-minute SLAM dataset, it's a whole different ballgame. In Ivion, if each dataset was using the same control network, they will more or less land exactly where they should, but a cloud-to-cloud adjustment is often used to look at both datasets and best fit them together. But if part of one dataset is stretched in the north-south direction compared to the other dataset you're trying to align it to, no matter what you do, the two won't agree to each other. Either the north ends align with each other or the south ends do. What some people will do in that situation is break the stretched dataset in half and best fit each half to the good dataset. But when you do this, you're not really fixing anything, you're more so just distributing or hiding the error. And you're probably also guessing which dataset is the correct one to align to. I asked NavVis if there was anything Frank could have done in the field to negate the issues we saw, to which they answered no. This was probably the scariest part of the whole thing. If they could have pointed to a break in the SLAM trajectory or something very obvious that caused this, I would have felt much better about the whole situation. They mentioned an alternate capture route would have produced different results. Whether or not that means better results, we cannot be certain of. And to make things worse, the company I worked for experienced very similar issues in our own data. In fact, during the filming of this video, we scanned a couple 100,000 square foot project halfway across the country with our VLX, and when it came time to QC the process data, we saw the exact same issues, only much worse. My takeaway from my conversations with NavVis was that you can do everything correct in the field, but SLAM isn't magic. There are going to be times when it fails. There are so many variables that go into SLAM capture and processing, it's pretty tough to entirely control each one. And part of what makes Ivion so easy to use, its highly automated processing, also makes it difficult to fix issues when they arise. To be clear, this isn't me trying to bash NavVis or Ivion at all. I'm a huge fan. It's just when you use SLAM, regardless of the manufacturer, we have to accept there are trade-offs versus terrestrial laser scanning. But the story doesn't end here. When I ran the one-dimensional method of accuracy determination, most of the site looked pretty good. Obviously, where check shots landed in areas of duplication, there were very large deviations, but the overall dataset was good. If only there was a way to get those individual datasets to talk to each other and fix these duplicated surfaces. Well, NavVis is currently working on a new tool that isn't available to the public yet, but remember how I said Ivion only does a rigid adjustment from one dataset to another? Well, let's just say this tool takes a much more nuanced approach. I can't say too much about it because it's still under development, but I can say after they ran this data through that tool, it almost completely removed the issues we saw. Let's jump back into NForce and look at the same problem areas we looked at previously. The red points are the first data set that we already looked at, and the blue points are the new data set that's ran through this new tool that NavVis has. As you can see, the new tool resolved the duplicated wall issues in almost every single instance that I could find. It really did a number on fixing this data set. Now for that other project I brought up a few minutes ago, some of the duplicated walls were almost half a foot out. There were no obvious slam breaks in the data, each dataset was tied to high quality control, and there was good overlap between datasets, yet the processing in Ivion produced an unusable dataset. I reached out to NavVis support to see if they could run the tool on that project, which they obliged. Now in that case, it didn't completely fix it, but it went from an unusable dataset to one that was within the accuracy spec requested by the client and saved us a remobilization across the country to recapture the site. If you've used a VLX long enough, there's a good chance you've encountered a similar issue, and knowing that a solution is right around the corner is pretty comforting. For the time being, if you are seeing these kinds of issues with your data, I would recommend reaching out to the support team of NavVis to see if they can run your data through this new tool on their end. And I just want to be clear, The issue NavVis encountered on the test site, or the one I saw on my project, is not typical. These are the exceptions. Much more often than not, the data comes out looking great and problem-free. I could show you hundreds of examples of beautiful, duplication-free data sets we've captured with our VLX. And this isn't really a NavVis problem as much as it is a SLAM problem. And NavVis has gone to great lengths to solve it. Other SLAM algorithms are susceptible to this same issue. Once I got the adjusted dataset back, I reran that through the one-dimensional accuracy measurement process, and the results were actually quite shocking. From the 126 check shots used that created over 2,700 check baselines, the VLX3 produced standard deviations of the residuals in each axis of 2 to 3 millimeters, with maximum deviations observed of about 12 millimeters or less in the northing and easting axis and 7 millimeters vertically. These are some pretty wild results. I had to go back a few times and double check I didn't screw something up. After the new tool was applied, the VLX3 produced a point cloud as accurate on this test site as either the Leica RTC 360 or Riegl's VZ600i when comparing planar features to other planar features. So walls to walls, floors to ceilings, etc. Essentially measuring the accuracy in a way that is representative of how this kind of scan data would typically be used for 3D modeling or vectorization. Now, I'm sure some people will question, how could it possibly produce a final point cloud more accurate than the specification of the LiDAR sensor it uses? After all, there's the ranging error of the sensors, error from the IMU, the registration process, tying in control, etc. And we're seeing final results after all of that that are better than just the ranging error alone. We cannot focus strictly on the accuracy of the Hesai XT32 LiDAR pucks. Not unlike the air propagation of a total station, the accuracy of a point I'm surveying can far exceed that of what is listed as the accuracy of the instrument, because random error can be reduced by the meaning of repeated measurements. When a wall was scanned with the VLX, we aren't getting every single raw point in the final point cloud. Remember, Frank scanned this site for 3 hours. That's 10,800 seconds of data. And given the VLX3 captures up to 1.3 million points per second, there was probably somewhere between 8 and 14 billion raw point measurements. The final point cloud I got was in the neighborhood of 2 billion points. A ton of points, and thus random error was filtered out. And by using the method of accuracy measurement I did, a lot of the noise left in the point cloud was neutralized by that least squares best fit plane tool of NForce that can define the center of planes in point cloud data very accurately. SLAM scanning has a very well-known tendency of smoothing sharp corners and smaller features. Shane McLaughlin, the managing director of Atlas Computers and the creator of SCC, who you may remember from my last tree digitization video, brought up a great point on the subject, which I would like to quote. When we look at data from a point cloud, whether manually by eye or photogrammetrically using an algorithm, we tend to get an average position for a given point based on the surrounding points. This average is calculated based on the assumed underlying geometry that the points represent. Example, on a section through a wall, they could be a best fit line. On a small area of a wall, they could be a best fit plane. On a pipe, they could be a best fit cylinder, etc. If the assumption relating to the geometry is correct, the effect of averaging or smoothing in the SLAM system is to remove random noise and increase statistical accuracy. If, however, the assumption relating to the geometry is incorrect, the effect of averaging can introduce a systematic error such as blurring small features. Hard corners are an easy to spot example of this. A potential problem with statistical analysis is that you could get a result where the SLAM is more accurate than the TLS for 90% of the points measured, but the critical points of interest in the survey lie almost entirely in the other 10%. Very well said. Shane brings up a few really good points here. Like I said, it's no secret SLAM smooths sharp corners. Some algorithms do it more than others, and NavVis data certainly isn't immune to this issue. He also brings up a great point about blurring out small features. If you've picked apart SLAM data, you know what I'm talking about here. The issue can be tough to quantify, but we can certainly use this dataset to draw some comparisons. I went back to the test site and took a video of a number of different sharp corners and small features that we will look at as I cut cross sections of the point cloud data. I will simultaneously show the same area of the point clouds that were captured with Leica's RTC 360 and Riegl's VZ600i. The VLX3 data is in navy blue, the RTC 360 is in cyan, and the Riegl VZ600i is in red. First up is a small conduit directly in the corner of a wall. Very tough conditions for SLAM. As we can see, the VLX data, or the blue points, smooth it out to a point where it would be fairly difficult to model it accurately. The RTC and the VZ do a decent job of defining the shape of the conduit. Next up is the stainless steel trim around the entrance of an elevator. The VLX and the VZ600i both really struggle here. I'd say the VLX does better than the VZ, but the RTC beats them both quite comfortably. Now let's revisit some vertical conduit, this time out in the open and leading up to an outlet box. The VLX almost completely erases the conduit here and smooths it into the wall. The VZ600i squared off the conduit for some reason, and the RTC actually did a pretty good job. Once we get to the outlet, the VLX rounded off the corners a bunch so that it almost looks like a cylinder, whereas the VZ and the RTC both approximate the true shape of the box fairly well. This next example is just a typical sharp concrete exterior corner, and the cross sections show a good example of what you'll typically see as far as the rounding of sharp corners goes when SLAM is used. The RTC data is pretty sparse here, but the VZ600 does have fairly nice sharp corners on the concrete, which accurately represents real-world conditions. This is a small grounding rod, maybe 3/4 of an inch in diameter. All the scanners really struggled here. The VZ and the VLX data are pretty much unusable. I think you could probably make use of the RTC data if you had someone skilled at doing the extraction. The next one is pretty tricky. There's a lot going on here. Same results though. The RTC data is the best. The VZ600i is right behind it with just a touch more noise that I don't really think would affect the usability, but the VLX really struggled. A lot of duplications, weird shapes, rounded corners, etc. One last one, some large diameter PVC drain pipes with fairly high albedo values. A situation where you would expect each scanner to do fairly well as far as round objects go, and the VLX did do a fairly good job here. The shape of the pipe isn't perfect, but with the right extraction tools, I don't think that would matter too much. Once we upped the diameter of the pipe, the VLX was able to define it pretty well. Not as good as Riegl's VZ600i, of course, but that shouldn't really be a big surprise to anyone. I have a bunch more examples like this, but it really is the same thing over and over. The VLX did a fantastic job at defining planes and larger rounded objects, but when it comes down to corners or smaller features, it's just not happening. If you caught my RTC versus VZ600i video where I compared the datasets that captured the bolt heads, you could clearly define every head of every bolt. The VLX is just not going to do that. You just have to understand what SLAM can do and what it cannot do. When it makes sense to use SLAM and when it doesn't. SLAM is faster, terrestrial laser scanning captures details better. SLAM registration is relatively easy and doesn't require a lot of input time. Terrestrial laser scanning registration allows you more control and reliability. It's not a one or the other answer, and as far as how the VLX stacks up against other SLAM scanners, it's a beast. No surprise there. The VLX3 is an obvious upgrade from the 2, and the 2 is great. Is it perfect? Of course not, but no scanner is. But so far, it's the best SLAM scanner I've reviewed on this channel. That being said, this is SLAM Wars, and we're just getting started. NavVis has some very stiff competition coming up, so we'll see how long it lasts as a champion. At the beginning of this video, I promised tips and tricks and technical explanations of exactly how the VLX and Ivion operate and what you can do to get optimal results. To do this, I found someone far more qualified to come up with these answers. I had a ton of questions for them, not only about this project, but about NavVis and Ivion in general. So I was able to talk them into giving me an exclusive interview where I hit them with some hard questions. Shout out to Rebecca Clark over at NavVis for putting in the effort on this project. Her answers were extremely thoughtful and thorough, so I'm basically just going to read out my question and read out her answer word for word, and if I feel the need to add anything on my end, I'll do so after her reply. I have my laptop here and I'm just going to read straight off of it. What techniques could one do in the field to ensure optimal scan data acquisition using the VLX? To ensure optimal scan data acquisition with the NavVis VLX, apply the following techniques in the field. Loop closures. Maintain consistent loop closures throughout the scan, ideally every 15 to 30 meters, with enough time elapsed between passes. These overlaps allow the system to recognize previously scanned areas from different angles and times, helping to correct drift and improve trajectory accuracy. SLAM-friendly environment. Ensure the environment contains sufficiently unique features and geometry to support stable SLAM tracking. In areas where such features are lacking, prepare the space by adding objects with distinctive geometry, such as a NavVis VLX hardcase or a backpack, to give the system something to localize against. This is what I was getting at earlier about SLAM not being able to work in every situation. We've tried to use it in open parking lots before and there was nothing we could do to get it to work reliably. We used our truck and other objects to help with the lack of geometry, which helped a bit, but at the end it was too unreliable to proceed with and we ended up having to use our RTC 360. Use of control points. Like loop closures, control points provide additional reference observations that help correct the trajectory, especially when operating only off SLAM during live capture and before all parameters are utilized during processing. Since the data collected is subject to drift and unavoidable accumulation of error over time, loop closures and control points act as benchmarks to readjust and stabilize the trajectory. However, if SLAM breaks occur during scanning, control points alone typically won't be enough to recover the dataset, as SLAM relies heavily on accurate initial localization supported by environmental features. Monitoring during capture. It's essential for the operator to watch the NavVis VLX interface during scanning. SLAM breaks can be identified by unnatural straight lines in the trajectory, erratic icon movement, or a collapse of the environment display that no longer reflects reality. These breaks are caused by external environmental factors and indicate a failure in the system's ability to localize. SLAM breaks cannot usually be corrected during processing. The system does not recognize that the data collected during a break is invalid. It will simply proceed with incorrect logic. The most reliable solution is to catch the break in the field, stop the scan, step back a few seconds, and start a new dataset. If breaks persist, assess the area to see if the environment can be improved for scanning. If not, it may be best to avoid scanning that section altogether. Trying to fix SLAM breaks after capture is time-consuming and rarely successful. Addressing them on site is far more efficient and increases the likelihood of a high-quality dataset. A helpful tip for the operator in the field is to review the quality map of the site. It will show if there were SLAM breaks or drift had occurred during capture. If something looks to be incorrect in the quality map, then that's a good indicator to rescan that section of the site before leaving. How does rotating in place versus smooth turns affect the algorithm? Example, stop, rotate, and continue versus rounding the curve and maintaining a constant speed. Smooth gradual turns are preferred because they help maintain a consistent walking speed and allow for a more gradual change in the LiDAR's field of view as the operator rotates. This is more favorable than a sharp stop and rotate motion, where the field of view changes rapidly, which can potentially lead to slam breaks. While this doesn't guarantee issues will occur, it increases the likelihood of a slam break, which will cause issues in the data. When investigating accuracy issues, one of the first things to examine is how the dataset was collected. If the operator moved faster than an optimal speed, the trajectory may appear in orange or red, depending on the severity. This trajectory indicator displayed at the top of NavVis's VLX screen when scanning reflects the quality of the field of view and functions similarly to an accelerometer indicating how smooth or erratic the operator's movement is. Because NavVis VLX includes an IMU, gradual or consistent movement is generally more favorable than jerky or abrupt changes in motion. What effect does scanning for too long have on processing? If I scan the same place with the VLX once in 2 half-hour scans versus once in a full-hour scan, will they be treated differently by the algorithm? The algorithm will not treat the datasets differently. However, a longer dataset has the advantage of providing more data, which gives the processing software more information to work with and can lead to better results. The longer the trajectory, the more opportunities there are for SLAM observations to be collected and potentially used to correct for drift if necessary. Shorter datasets are allocated fewer processing resources in the cloud, which can result in faster processing times due to the smaller, less resource-intensive tasks required. From an accuracy perspective, a longer dataset does not negatively affect the results. A longer dataset will require more processing resources and may take longer to begin processing once current available processing capacity is freed up. But aside from this increased processing time, there is no disadvantage to capturing a longer dataset. In fact, we encourage you to do so, as it provides additional loop closure observations that can help correct drift throughout the dataset, something that would not be fully achievable with 2 shorter separate scans. What can you tell me about optimal control density and how control points are applied to a dataset? Is control always 100% needed, and if so, how accurate should it be? Control points should be placed no closer than 5 meters from one another to avoid conflicting influence on the trajectory. Since control points function similarly to loop closures, providing correction values to our processing algorithm, the optimal density depends on the trajectory taken. Loop closures are typically spaced 15 to 30 meters apart based on geometric distance from the previous closure, and control points should generally be spaced every 25 to 50 meters. Because both loop closures and control points serve to generate correction values, quantifying the observed drift between 2 timestamps, they are treated equally during processing. In environments where loop closures are not possible, such as long corridors or open areas with minimal features, control points are strongly recommended. However, it's important not to assume that control points and loop closures alone are sufficient to remove slam breaks in challenging environments. The foundational requirement for successful slam remains the presence of unique static geometry. Control points are used to supplement and assist in correcting slam drift, not to replace the need for suitable scanning conditions. Control points serve as external benchmarks against which slam observations can be compared. This means that the more accurate the control point is, the more effectively it can be used during processing. However, any inaccuracies in a control point, such as those introduced by surveyor error, can be artificially introduced into the trajectory during processing. In other words, a poor quality control point can introduce error in the scan that wouldn't have existed prior. The allowable difference of coordinate position between the internally captured control point from the VLX and the externally provided control point is 3 meters. meaning it's possible to introduce error into the trajectory if there are inaccuracies in the external control point being provided and the deviation of the point is less than 3 meters. This 3-meter tolerance refers to the allowable deviation between the externally provided control and the control captured by NavVis VLX. It exists because we expect some inherent error in SLAM data known as drift, which are unavoidable errors that accumulate over time. A deviation of up to 3 meters is not unrealistic. However, the closer the deviation is to that upper limit, the more likely it is that the control point is unreliable, either due to miscapture in the field by the NavVis VLX or by human error. In such cases, we recommend excluding that control point from processing by disabling it during setup and review of the control point configuration. Our control point application process consists of 3 stages: alignment, verification, and optimization. Alignment is a rigid transformation where the external control points are aligned to the dataset without applying any distortion to the NavVis VLX captured control points. Residuals at this stage are expected to be the highest of the entire process. Verification begins to apply some, but not all, of the control points. This is intentional as the goal is to observe how introducing select control points affects the trajectory in the resulting SLAM-based environment it has generated. Optimization is the final and most important stage. This is where all control points are applied to the dataset, resulting in the tightest residuals. The aim is to bring these residuals as close to 0 as possible, meaning there is no observable deviation between the NavVis VLX captured control point and the externally provided ones. Control points are not always required. They can be used interchangeably with loop closures, but the key takeaway is that consistent correction values must be present throughout the dataset, whether achieved through loop closures or control points. These corrections are essential for maintaining a high level of accuracy. So that whole 3-meter deviation between where the VLX thinks a control point is and where the survey network says it is usually comes into play with a mislabeled control point. If your scan fails because of the control point being applied, make sure you check your point number labeling. Rebecca's note about control points are not always required and can be used interchangeably with loop closures is interesting. I will add one thing: we've tested the VLX quite a bit with varying levels of control being applied in different situations. Control may be required depending on variables such as accuracy spec, site size, and the physical environment you're working in. If you have 2 walls in the raw SLAM data and the algorithm needs to figure out, is wall A in the right position, maybe wall B, maybe it's the average of the 2 or some other statistical variation of that, it's tough to solve that problem without external survey control points nearby. How long did it take to process the garage datasets? If possible, could you give me 2 times? Total processing time and user input time. User input time, less than 5 minutes to set up the processing task and begin processing, estimated as this was not tracked. Total processing time, the first dataset was about 8 hours, the second dataset was 15 hours, and the third dataset was about 7.7 hours. Now, I don't really think total processing input time on this project was 15 minutes. There's data download, there's data management, control file management and conversion, alignment of multiple datasets, etc. But this is one area where NavVis really has an advantage over terrestrial laser scanning. There's no reason it should take someone hours of input time to process a NavVis job in Ivion unless something goes wrong and they need to troubleshoot or fix data, which can actually be a very tedious process, or you're aligning a large number of datasets that aren't on control. Besides that, it's really easy and input time is very low. Sure, this project took 31 hours to process, but it's being done in the cloud. It's not even taking up a workstation. It's really a non-issue 99% of the time. Is there a process available to clients to merge NavVis data with other point cloud data? Can it be done directly in Ivion? Yes, in fact, it's incredibly easy to do so. NavVis Ivion supports various point cloud file formats, and the exact workflow is described here. I'll add the link to the description. If the datasets have already been georeferenced, then the external scans will be automatically aligned when uploading via the dataset management. If they have not been georeferenced, you can manually align them by following the same steps used for aligning any manually added NavVis dataset. Once aligned, the project in NavVis Ivion can be exported as either a unified E57 file or as individual E57s using the crop and download tool, depending on which datasets are toggled on in the dataset tree on the right side of the tool. This feature can be really handy on sites where you scanned part of it with a VLX and part of it with a drone, terrestrial scanner, etc. Let's say you used a drone to scan the roof of a building and a terrestrial scanner on an extendable tripod to get above ceiling elements. You can bring your data into Ivion for alignment and compilation into a single dataset. How does the pay-as-you-go system of registration work with NavVis? What made NavVis decide to go this route versus a more traditional payment system such as a yearly subscription or perpetual license? Is this something NavVis offers? NavVis Ivion processing is licensed through annual volume-based packages of processing units, a unified metric that can be flexible across a variety of tasks, including processing data from different NavVis devices, blurring panoramas for privacy and compliance, and potential future features. The decision to adopt this model was driven by the need to simplify licensing across our diverse solutions. Instead of purchasing multiple licenses for processing data from the NavVis VLX3, the MLX, and for blurring activities, customers can now benefit from a single metric that applies to multiple processing tasks. This unified approach gives customers the freedom to allocate resources where they are needed most, simplifying usage management. Additionally, our usage-based business model aligns NavVis's success with the success of our customers. The more square footage the customer captures, the more value is derived from the platform. This creates a mutually beneficial win-win relationship. I'm going to be honest here, this answer sounds like it came straight from the sales team. I can register multiple devices from a different manufacturer in a single piece of software on a single license and blur faces without them needing to switch to a token-based system. I would also imagine having a reliable and continuous revenue stream is also very important to the viability and financial security of NavVis. I've said it before, I'm just not a fan of the pay-as-you-go model. But I'm also not in business. What do I know? It probably was the right move for the company. They've managed to grow and innovate extremely fast and build one of the best family of SLAM scanners and online platforms in the market. This choice probably gave them the financial security to put R&D dollars into making that happen. But that doesn't mean it doesn't bug me. Does it bug me enough not to buy a VLX3? No, certainly not. If a competitor came out with a scanner just as good in every way that cost the same but offered a $5,000 perpetual license, would I make the switch? Yes, I would. But NavVis makes a hell of a scanner, so that day may never come. What was the cost to process this site if the user purchased the largest amount of tokens possible and got the best price per token possible? With our largest volume package, the cost per processing unit is $0.00093 per unit. For processing NavVis VLX3 data without blurring, the consumption rate is 25 units per meter squared, resulting in $0.0022 per foot squared. So if my math is correct, that means for the 250,000 square foot test project site, that would have cost $550 to process. It's really not much in the grand scheme of things. Let's say it took me an hour or two of processing in data management time to turn the raw data into a process point cloud with a VLX. What would the break even be if I had to pay someone $40 an hour to process scan data that took a more user-intensive approach? That would be around 16 working hours. Now, should it take someone 16 working hours to process this site with, say, the VZ600i or an RTC? No, it really shouldn't. But you're also paying $4,000 a year for Register 360, so you have to factor that in as well. Again, I would rather buy once, cry once with software, but it's not the end of the world. It's mostly my deep-rooted frugality that makes me struggle with this issue. What is the cost of a NavVis VLX3, a typical out-the-door price after fees? The typical price in US for a NavVis VLX3 kit is $76,500. However, the overall solution cost can vary depending on the customer's specific needs, particularly regarding Ivion software subscriptions. These software components are tailored to different usage levels and project requirements, which can influence the final package price. If issues are observed during registration, let's say duplicate walls or ceilings, such as what was found in the first dataset I got back from you, how much control do users have to fix those issues, and what does that process look like? While support is always an option, customers often prefer to try resolving these issues on their own. The first step is to examine both the unprocessed and processed quality maps. The goal is to determine whether a specific dataset is solely responsible for the duplication of features. Typically, the answer is yes. In such cases, review the quality maps again, but this time focus specifically on the trajectory. Try to identify the moments when the duplication occurred and check whether the trajectory is colored in orange or red. These colors indicate potential degradation in SLAM observations, often caused by operator actions. In addition to the trajectory color, the shape of the trajectory and any signs of wobbliness can be equally, if not more, informative. The IMU in NavVis's VLX system is highly sensitive, meaning it captures the operator's specific gait and reflects it directly in the scan. Moments where the trajectory appears extremely erratic or unnaturally straight typically signal a SLAM break. All featured duplications are the result of SLAM failure. The primary culprit is usually a visible SLAM break, which can be identified in the quality reports or maps. The Define Processing Time Frame tool can be used to remove these problematic portions of the trajectory. This will result in two separate scans that are each accurate on their own and can be manually aligned using overlapping geometry with our automatic cloud-to-cloud alignment tool. These visible SLAM breaks usually last no more than a second, as a more severe breakdown will be noticeable to the operator, who should stop the scan if that occurs. We've had to deal with this process before, and it's not ideal. As has been already said many times before, review the data in the field, and if you see an issue, recapture the data. You'll be 10 times better off doing this. What kind of situations would the VLX3 struggle to capture data in? What situations does it excel in? NavVis VLX is a SLAM-based scanner, meaning it relies on unique geometry in the environment to act as reference points from which the system can determine its location. Because the system depends on this unique geometry to operate and track its position accurately, such geometry must be consistently present within a 50 to 60 meter range. If it isn't, the system will lose localization. Areas that do not meet this requirement result in SLAM breaks. These breaks are not recoverable or repairable, and the affected portion of the trajectory must be removed using the Define Processing Time Frame tool to correct the data. SLAM will struggle in environments that are homogeneous or lack distinct features, such as long, straight, narrow tunnels or hallways with no variation in geometry. It also struggles in wide open areas like fields where there are no vertical surfaces. Trees, for example, typically do not provide sufficient planar surface area at the necessary angle of incidence. Their usable planar area is often less than 30 centimeters by 30 centimeters, which is insufficient for localization. That said, these environments can still be workable if the operator introduces unique geometry into a scene. A NavVis VLX hardcase works great in these scenarios. We already touched on this subject of having mixed results when introducing objects in scenarios that lacked geometry themselves. I've noticed that the NavVis data tends to round off sharp corners or miss smaller details, sometimes merging them into a corner if it's nearby. Is there anything a customer can do during capture or processing to mitigate this, or is it just part of dealing with SLAM scanning? NavVis data does tend to round off sharp corners, sometimes missing small details, like a conduit in a corner, which might get merged into surrounding data. However, there are steps the customer can take in the field to help mitigate this. Capture as many fields of view as possible from as many angles as you can. Our filters are designed to remove fringe points, edge points, mixed pixels as much as possible to ensure you get the cleanest data. This difference becomes especially clear when you compare SLAM data captured from a single angle versus from multiple directions. A good example would be the difference between a U-shaped pipe from limited angles and a properly rounded pipe when captured from all sides, or when points appear to blast past a corner until you actually walk around it. Without those extra perspectives, the system lacks the information needed to filter out inaccurate points. If you're aiming for the highest level of detail, make sure to process the data using the high confidence setting. This is what we recommend for complex spaces, both because of improved data quality at range and the more aggressive filtering it applies. To some extent, rounding is an inherent limitation of SLAM scanning. It's a factor in all SLAM-based data, including ours. That said, when scanned properly, the level of detail NavVis can maintain is greater than what's typically lost. In fact, NavVis is among the best at preserving small details from SLAM data. And we already talked about this and looked at some examples previously. It's a well-known issue of SLAM, and if anything, in the datasets I've personally looked at, NavVis preserves more detail than most other SLAM solutions I've explored. Not all though, which we will see in the second episode of SLAM Wars when we start digging into the ZNF FlexScan data. I've noticed when cropping and downloading a point cloud from Ivion, it can take a substantial amount of time to crop from an RCP format versus an E57, sometimes into the double digits of hours. Is this normal, and is there a way around this delay? We rely on an Autodesk SDK to export RCS file formats. However, this SDK is currently compiled only for Windows. As a result, we must perform an internal conversion with our product to enable direct RCS exports, which significantly slows down the process compared to exporting to an E57 format. Ivion's based on Linux. There is a forum petition on Autodesk website requesting broader SDK language support. If you're interested in contributing, you can find it here, and I'll add the link to the description. A Linux-compatible SDK would significantly improve export performance for recap file formats from NavVis Ivion. A faster workaround, we recommend using the E57, including panoramas, export option from the crop and download, then importing that file into recap and exporting it as an RCP/RCS from there. Considering the Riegl VZ600i can capture static scans with imagery in between 20 to 40 seconds depending on density settings and lighting conditions, do you feel that this speed of capture can start to replace some use cases for SLAM scanning? The Riegl VZ600i is a great scanner. It captures data in around 30 seconds, including imagery, and its compact form factor makes it much more mobile than previous Riegl models. Given its field of view and the density of the data it captures, this scanner is best suited for lower detail applications. That said, there are scenarios where a fast TLS like the VZ600i could serve as a replacement for SLAM scanners. Just a butt in here, it's interesting they mention it's best suited for lower detail applications when it's pretty obvious terrestrial scanning is capable of much higher detail captures, but I'll keep quiet for now. One clear limitation of the VZ600i is that it cannot capture data directly overhead. As a result, you'll need to increase the number of setups in indoor environments, especially complex ones, to compensate for this missing field of view. In environments without overhead abstractions, the VZ600i performs very well and could be a viable alternative to SLAM scanning. However, if you apply the same approach indoors, the VZ600i is likely to be quickly outpaced in terms of efficiency and completeness. Okay, so I'm going to push back on this answer. I've explored the impact of the overhead cone of occlusion from the VZ along with the zone of occlusion under the scanner. It has an impact, but rarely to the extent where those missing zones are not filled in from other nearby scans. I asked this question because I wanted to hear their perspective on what I view is going to be some serious competition, not only for the NavVis VLX, but all SLAM scanners, high-speed terrestrial scanning. It took Frank about 3 hours to scan this site. It took me about 550 scans with the VZ, which worked out to just over 10 scan hours. So the VLX was about 3 times as fast. And that adds up on bigger projects, and Frank was able to walk more places than I set up my tripod and scanned. The VLX dataset has better coverage and less scan shadows. I like to think of it like this. When you're using SLAM, you're more or less taking a scan every step you walk, versus when I use a tripod and scanner, I'm getting discrete scans every 5, 8, or 10 meters. There's no fighting it. You're either going to have way more scan shadows using terrestrial laser scanning or take way longer in the field. Now the VZ dataset is pretty complete and 100% usable to model or vectorize, but it's not as complete as the VLX data. It's going to be hard to beat SLAM in terms of speed, and SLAM will also have better efficacy on situations where the ground isn't stable, and I'll tell you, those ramps in the parking garage jumped around like crazy when a car drove over them. I must have had to redo about 20 scans on those stupid ramps from cars driving by until I decided to start blocking them. One other factor to consider, SLAM is generally going to require more control to obtain similar levels of accuracy. So there's many layers to this discussion. So should you go out and buy yourself a brand new shiny VLX3? Well, it's one hell of a scanner at a fair price with great support. It's hard to go wrong if you have jobs that are conducive to SLAM scanning, which not all jobs are, and this is extremely important to grasp. I will say, if I made this video 6 months ago, before they had this new tool coming out that is capable of fixing the registration errors we have experienced in the past, I would have had a tough time emphatically recommending the VLX. It was still a great package, but this new tool that's being introduced to Ivion is going to seriously increase the reliability of the VLX. It's still not the right tool for every job, but if you know when SLAM is appropriate to use, it's a fantastic choice. Now, before you call them up and drop $75,000 on a new scanner, we still have a few more SLAM scanners to look at. Next, we're going to explore ZNEF's FlexScan, a scanner that doesn't make you choose between SLAM or terrestrial scanning. You can use SLAM when you want the speed it can offer and swap over to terrestrial scanning when you need those finer details and higher reliability. But can it stand up to the VLX? You'll have to tune in a few weeks to find out. Thank you all for watching, and as always, subscribe if you want, like if you feel it's warranted, and I'll see you next time.